Hi, dear friends, welcome. Today we will discuss about the selection sort. Having seen how to search for an element in the array, and now let us turn to sorting. So, the most basic motivation for the sorting comes from the searching. As we have seen, if you have an unsorted array, you have to search for it by scanning the entire array from the beginning to the end. You spend linear time searching for the element, whereas if you had sorted array you can probe it at the midpoint, use binary search and achieve the same result in the log time, and log time is considerably faster than a linear time. Now there are other advantage to having the elements sorted. For instance, if you want to find the median, the value for which half the elements are bigger and half the elements are smaller, well, the median of a sorted array is clearly the midpoint of an array. If you want to do some other kind of statistical things, such as building a frequency table of the values, when you sort these values, they all come together, right? So all the equal values will be in the contiguous block. So it is much easier to find how many copies of each values are there. And in particular, if you want to only one copy of the every value, if you want to remove all the duplicates of the array, then you scan the sorted array from the beginning to end, and for each block of value keep just one copy. So there are many different reasons why one may want to sort an array to make the further computation on the array much easier. So let us imagine how would you like to sort an array. So forget about array and think about the sorting something which is given to you as a physical collection of objects. So say you are a teaching assistant for a course, and the instructor, the teacher who is the teaching the course, has corrected the exams and now wants you to sort the exam papers in order of the marks. So say your task is to arrange them in the descending order. How would you go about this task? So one nice strategy is following. You would go through the entire stack and keep track of the smallest mark that you have seen. At the end of your pass, you have two paper in your hand, which has the smallest mark among the marks allotted to all the students. So you move this to the new pile. Then you repeat the process. You go through the remaining papers after having the discarded the smallest one into the new pile. Look for the next smallest one. Move that on top of the new pile, and so on. So after the second pass, you have second smallest mark on the pile. Up to the third pass, you have the third smallest mark on the pile. As you can imagine, after the n passage, you have moved all the n papers from the old pile to the new pile in the descending order. So this particular strategy can be illustrated as follows. So supposing we have the list of array of the six elements. So in the first pass, we look for the smallest value. So the smallest value in this case is the 21. We move 21 to the new list and remove it from the original list. Now we repeat the scan among the remaining values. The value 32 is the smallest one. That value 32 is the smallest one, so we remove that and move it to the new list. We keep doing this. So at the next step we move 55, and then we move 64, and then we move 74, and then we move 89 to the right. So in this progress process, if this had been a vertical stack, 21 would be on the bottom and 81 would be on top. So we would have the list sorted from top to bottom in the descending order. In this case, it is from the right to left in descending order, or from the left to right in ascending. So this strategy is called the selection sort. So we select in each round the next element which is the smallest, and therefore the next we put out in the sorted order and move it to its correct position. That is to the end of the final sorted list. No, this version of selection sort that we just described builds the second list. In other words, in order to sort one pile, we have to create a second pile of the papers. Now we can easily enumerate the second pile of papers if we do the following. When we find the minimum element, we know it must go to the beginning of the list. So instead of creating a new list, we move it to the beginning of the current list. Of course, in the beginning of the current list, there is another value. So we have to do something with that value. You just exchange that position. So we find the minimum position and swap the values at that minimum position with the values at the first position. Now, the smallest value in the entire array has moved to the beginning. So now we want to start from second elements onwards and look for the minimum. Again, this will be the second smallest. So we now having found that we will move that in the second position in the array value. So we keep doing this, and without using a second list, we are able to do the same sorting that we did before. So to see how this works, we take the same array that we had before. As we said in the first round, we identified 21 as the minimum element, which is marked in the red. And the first position is the 74. So we would like 21 to be the beginning of this list. So the since 74 is there, so we access the 21 and 74 and we get this new list. In this new list, now 21 is marked in the green to indicate that it's a final position. It is the smallest value. It is moved to where it should be in the sorted list. So now we scan the remaining element and we identify that 32 is the smallest element. Now 32 already happens to be in the second position. So we could think of exchanging it with itself and doing nothing depending on how you want to interpret it. So 32 now becomes marked in green, so that it say it in the correct position. Now in the remaining list 55 is the smallest element and marked in the red, but it has to be at position third, which is occupied by the 89 marked by the yellow. So we exchange these two and now we have 55 in the third. So we keep doing this. So at the next step we will identify 64 and swap it into the fourth position, and then we find the 74 is already in the correct position, so we leave in it where it is. And finally, of course, 89 is the only element. So when you have a list of one element, there is no sorting to be done. So this procedure can be described by a very simple iterative algorithm. So what we do is that we have, if you remember, we start by scanning the entire array, that is from 0 to n minus 1. We look for the minimum element in the segment, right? So we have an iteration which basically start at the starting position, and then from the starting position onward it assume that the beginning the is the minimum value, and wherever you find a smaller value you mark that as a minimum position. Now having done all this right, we have now found the minimum from a0 to a n minus 1. Then you move this value to the beginning, so you swap the starting position and the minimum position. Now we have the smallest value at a0. So now you go back to this loop and now you move starting position from 0 to 1. So you do the same scan for the a1 to the n minus 1, right? And now starting position is 1. So at the end you swap the second smallest element a1, then you do it for the a2 to the a n minus 1 and so on, right? So this is the simple iterative version of selection sort, where we just start with the entire array, move the smallest element to the first element, first position. Then we take the rest of the array from a1 onwards, move the smallest element to the a1, then start with the a2, find the smallest element, move a2 and a so on. So how much time does the algorithm take? So clearly, in order to find the minimum elements in unsorted segments of length a, we have to scan the entire segment of this text, and in each iteration the segments to be scanned reduced by 1. So we start by scanning all n elements, then we scan n minus 1 elements, then we scan n minus 2 elements, and so on. So we have over all the number of steps is n plus n minus 1 plus n minus 2 down to 1, which is just the usual summation. I is equal to 1 to n of I, and this we know is n into n plus 1 by 2, which is order of n square, right? So this nav algorithm selection sort is the iterative implementation is the n square. Okay, thank you.